Hey there, everyone. Most recently, we've dealt with the quadratic formula in terms of a really useful tool because it allows you to solve any quadratic equation. We're just going to dive a little bit deeper into that realm here, revolving around this idea called the discriminant of a quadratic equation. So what you'll see in the graph right here are three graphs that are all parabolas, and so therefore there are some quadratic functions, right? Some equations that will make each of these three different graphs. They're in different colors. You can see the first one at the left there is in green, the one in the middle is down there is in blue, and then the last one at the right there is in red. And that does correspond to the colors that I have here as well as the red, blue, and the green. So I will start with the red one, so with this particular parabola right here. So with this red one, its equation is y equals x squared minus 6x plus 5. What I'm going to do with this equation, as well as all of the other equations, is I'm going to work to try to find the zeros of the function. So by definition, right, zeros are the x's that you can plug into the function that will make the y equal 0, right? So that means that if we want y equal to 0, then we can plug in a 0 for y and then try to solve this equation. And yeah, so it turns out that this is quadratic, right? So we could use quadratic formula. So yeah, let's try to use quadratic formula to do so. So we know based on the quadratic formula that x is going to be equal to negative of b, so negative of negative 6, plus or minus the square root of b squared minus 4ac. So we can plug in, we've got a 1 right there for x in front of x squared, and then a 5 there for c, and that's going to be all over 2 times a, so the 1 there for the a. Okay, so what this is going to simplify to then is negative 6 makes positive 6, and I'll write that over the 2 times 1, and then plus or minus, so we're going to get negative 6 squared, which is 36, and then the 4 times the 1 times the 5 is 20, and there's only one negative in there, so you will truly subtract then 20 from 36. That's going to be over 2. So this will really just boil down to 3, because that's what 6 divided by 2 is equal to. And then under the square root, you'll have 36 minus 20, which is 16. But we actually know that the square root of 16, right, is actually 4. So I'm just going to write that as plus or minus 4 halves. But then we know 4 halves is actually 2, because 4 divided by 2 is 2. So we get 3 plus or minus 2. So 3 plus 2 is 5, and 3 minus 2 is 1. So you actually get those right there are going to be the zeros of the function. So those are the numbers that you could actually plug into the equation. So for example, right, you could plug in 5 squared minus 6 times 5 plus 5, and then y would equal 0, right? And the same thing would be true, not only if you plugged in 5, but you plugged in 1. That makes sense based on the graph that we're seeing right here, because you'll see that right there at 1, comma 0, right, for y. And then right there, 5, comma 0, right? Those are the zeros of the function, right? So we get some zeros that are actually real numbers, right? And that corresponds to seeing that it crosses to the x-axis, right? So if I were to do the same thing with the green parabola, let's say next, right? If I wanted to find the zeros of the function and I have the graph, well, I can see easily it's got an x-intercept on negative 10, right? So it's got to be a 0 of the function. And it does turn out to be definitely a 0 of the function. So I want to go to that green one right here. So that's the third column here. So let's plug in a 0 for y, because what that would do is allow me to try to find the zeros of this function. So I plug in a 0 for y, and then it's quadratic now. So let's use quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4, a again is 1, and c is 100, and that's going to be all over 2a, so 2 times 1. So we end up getting then negative 20 plus or minus the square root. 20 squared, or 20 times 20 is 400, and then the 4 times 1 times 100 is 400, so you end up getting 400 minus 400 underneath that square root. That's over 2 times 1, so over 2. So we end up getting negative 20 over 2, so negative 10 plus or minus the square root of 0 over 2, right? But we know the square root of 0 is 0, because 0 times 0 is 0. And then 0 halves is actually 0, so then we actually are plusing or minusing 0, and negative 10 plus 0 is negative 10, and negative 10 minus 0 is negative 10, right? So you just get negative 10 as the only 0, right? It happens to be a real number, right? Yeah, beautiful. Okay, so now if we go to the last blue one right here, right, you might think about, okay, if I'm going to find the zeros of this function, right, it turns out it does have zeros, okay, but they aren't going to be real because it's not crossing the x-axis, right? There's no point at which this graph crosses the x-axis, so there are no real zeros of the function, but there are some zeros, okay? There's going to be some imaginary complex number sort of stuff that is going to happen right here. So if I were to find the zeros of the function, I would first of all plug in a 0 for y, and then we can use quadratic formula right away because all your terms are all on the other side of the 0. So yeah, x is going to equal to negative of b, so negative of negative 6, plus or minus the square root of b squared, so negative 6 squared, minus 4ac. Now it turns out that your a is a negative 1, and then your c is a negative 13. So a lot of negatives, and that's going to be all over 2 times a, so 2 times negative 1. So simplifying this all, negative negative is positive 6, plus or minus the square root. So if you do negative 6 squared, you get 36. And then 4 times 1 times 13 is 52. And then because it's a negative times a negative times a negative, an odd number of negatives times, it's truly negative, so we're going to subtract. And then over negative 2 on the bottom, right? So it's really like 6 over negative 2 plus or minus the square root. If you do 36 minus 52, you get negative 16. That's going to be over negative 2. So this negative 2 really matters because 6 divided by negative 2 just gives you the only answer of negative 3. The fact that that's a negative there doesn't really matter because you're plusing and minusing, right, that second fraction. So it's not really that important, right? So you just end up plusing or minusing. The square root of negative 16 is going to be imaginary, right? It's going to be square root of 16 times I, but since the square root of 16 is 4, it just ends up being 4i over 2. And if you do 4 divided by 2, you actually get 2i. So that means that x equals negative 3 plus 2i, or x equals negative 3 minus 2i. So either that first number or that second number are going to be the zeros of the function, okay? So there's some interesting things that we can tell on all three of these examples, like in terms of knowing whether the zeros of the function are real or if they're complex. And if you really think about how you get complex numbers, right, the only way you're going to be able to get a complex or an imaginary number is if you are going to like square root some sort of a negative number, right? That's where you're going to get an imaginary number. And so when you look at the quadratic formula in general, there's only one place where we have our square root, right? And you can see I'm going to highlight right here. I put that little blue blob right there, right? That's where we got a negative under the square root. And that thing under the square root that's negative is going to make it ultimately be imaginary, right? Versus if I make another blob there in the green, we actually got a 0 underneath the square root, right? And that 0 is kind of important because then that means we're plusing or minusing nothing, which just then left us only with just that single number before the plus and minus, right? So that kind of tells us like when the graph is going to, just hit the x-axis just once. That's kind of a significant to note. And then finally, in the very first case, in the red case, when we actually got something underneath the square root, so putting that red blob right there, that was positive because we got 16. That meant that we were actually going to get two different real answers, right? Because if it's a positive under the root, it's real, and you're going to plus or minus it. So you're going to get two different real number answers, just as we did right there, okay? So what's happening underneath that square root in the quadratic formula is so important because it tells us whether we're going to get real or complex answers, as well as the number of real or complex answers that we're going to get. It's so important that we actually call what's underneath the square root a name, and we call it the discriminant of a quadratic equation. So it turns out that the discriminant of a quadratic equation, so if that quadratic equation is in the form number times x squared plus number times x plus c, and it's equal to 0, And the parentheses is right there just to acknowledge the fact that we got to make sure that a is not equal to 0, because then it wouldn't be quadratic, right? We want a to at least be something that's a number not 0. So it turns out that the discriminant of a quadratic equation like that is the value of the expression, the thing that's under the square root in the quadratic formula. So it just turns out that the answer that you get when you do b squared minus 4ac, okay, just the part under the square root. So there's not a square root. We're not square rooting, just the part underneath the square root. That gives you the value of the discriminant. It's really, really useful for us, and like I said, in determining whether or not we're going to get complex answers or real answers or whatever it might be, right? So the reason why it's called the discriminant is it allows us to discriminate like what types of solutions you're going to get, whether they're going to be real solutions or complex solutions, as well as the number of solutions. So one useful thing is to know if we get either real or just strictly complex zeros in a quadratic equation. And then also it tells us how many unique zeros we get, because sometimes we get just like one real one sometimes, okay? So you'll be able to tell kind of a lot of things using the discriminant. So I'm just going to draw kind of 3 different parabolas right here and talk about the values of the discriminant that we're going to see here. So if you have a parabola that, say, does this, right? So it's like an upside down parabola. The discriminant, so b squared minus 4ac, the discriminant actually has to be positive whenever it crosses the x-axis twice. So if there are 2 real x-intercepts, that discriminant is going to be positive, okay? Now, if you have another parabola that's, let's say, is this parabola right here, and it only hits the x-axis once, okay, then it has a 0, and it's a real number, whatever that x number is right there. That means that the discriminant, its value is equal to 0, okay? And so the last case is then whenever that discriminant is a negative number, then that means that there are only complex zeros, which means that the parabola will never ever hit the x-axis. So if the parabola opens down, that means it's got to be like somewhere below the x-axis to never cross through the x-axis. But if the parabola was like a facing up parabola, it would just need to be somewhere like above the x-axis, right? So there's 2 different examples where the discriminant, or in other words, just b squared minus 4ac, would be a negative number, okay? One thing I do want to bring to your attention too is sometimes this symbol right here looks like a triangle, but it's not, is used to represent the discriminant. It's actually the Greek letter delta, so it'd be kind of like their 4th letter of the Greek alphabet. That's oftentimes used to signify the discriminant, so I may use that. Really just means that it equals b squared minus 4ac. Okay? All right. So, taking a look at some examples where we can kind of apply and bring all this information together. So it says right here that we want to find what the discriminant is, right? So we'll see some examples of that, and then see how we can actually use that discriminant, that number itself, to determine the number of solutions that there are to the equation, the number of unique solutions, really, and then what types of solutions we're actually going to get out of this, okay? Okay, so with this first example right here, okay, what I'm actually going to do with this, though, is I'm actually going to, make that side be a 0. And so now if we were to solve this equation, we could use quadratic formula to do so, right? And so since you've got all your terms on one side and you know exactly that your a value is -9, your b value is 6, and your c value is -1, right? Then all you need to do to find this discriminant, I'll use that delta symbol, is just do b squared minus 4ac. So if you do b squared, you're going to do 6 squared minus 4 times a times c. Then you're going to get 36. And then if you do 4 times 9 times 1, that's 36. And then a negative times a negative times a negative is subtracting. So you're going to subtract 36. It's going to equal 0. So that right there is the answer of what the discriminant is. Okay, the discriminant is just a number, right? It's just the number that you would have under the square root if you were actually solving using the quadratic formula, right? So if we were actually finding the solutions, in other words, solving this equation, and if we were using the method of the quadratic formula, you would have x is equal to negative b, so negative 6, plus or minus the square root. But then we already figured out b squared minus 4ac, right? Because the discriminant is 0 all over 2 times a, right? And then you would just like keep simplifying that and you would get your solutions, right? Now, what it really means though is that when you get a discriminant of 0, that means like you're plusing or you're minusing ultimately nothing. So whenever you get a discriminant that is equal to 0, what that means is you only get one solution. So you're going to get exactly one unique solution. And the solution type that it will be in terms of it, whether it's real or complex, is that it's going to be a real number, right? So like if you were to graph that parabola where y equals negative 9x squared, like it would just be a parabola that touches the x-axis once, like sits on the x-axis. So yeah, there's just going to be exactly one unique real 0 or solution for that function, for that equation, okay? Okay, so if we jump to this equation right here, you've got terms on different sides. So in order to use the quadratic formula and also find its discriminant, you've got to have all the terms on one side. So if I rewrite this where I subtract 7x to both sides, then I'd have 1/2 x squared minus 7x plus 25 equals 0. And then use that as a being 1/2, b being negative 7, and c being 25. So the discriminant then would be equal to b squared, so negative 7 squared, minus 4 times a times c, like that. So we'd end up getting 49, because that's negative 7 squared. And then if you did 4 times 25, that's 100, and then half times 100 is 50, so it'd be 49 minus 50, which is equal to negative 1. So that right there is the discriminant, okay? So what that means, right, is this would be the number that would go underneath the square root if you were using quadratic formula. So negative b plus or minus the square root of negative 1 all over 2 times a, right? So that means that, oh, we're going to get imaginary solutions because we got a negative number, right? So anytime that discriminant is negative, you know you're going to get complex solutions. So we will get complex solutions. This is the meaning of that discriminant. And you're going to get exactly 2 different ones. So I'll say that we'll get 2 unique complex solutions, right? So we're just using that number negative 1 to deduce kind of the types of answers we're going to get, right? And that's all. All right, and then finally for this last one right here, all the terms are on one side as quadratic, and you got 0 on the right-hand side, but notice how it's kind of out of order, like your a is there actually, and your b is there, and your c is there, so just be careful about that. So yeah, the discriminant would be equal to 1.4 squared, since that's b, minus 4 times a times c. And all right, well, that's going to be 1.96. And then, yeah, if you times all of that stuff out right there, you're going to get, well, it's going to be positive. So you're going to plus something, and it doesn't really matter what it's going to be, because if it's positive, that can tell us exactly the type of solutions we're going to get. All right, I guess we should figure out what the number is, so let me type this in. Okay, so plus 39.04. Okay, oh, that's a nice whole number. So that gives you 41. Okay, that's the discriminant. So what I meant by saying, okay, it doesn't matter, is like, it's going to be a positive answer right here, and no matter what type of number you get, as long as it's just positive, what that means then is when you're using the quadratic formula, you're going to get a 41 underneath that square root, that positive number in the square root. So you're going to end up getting 2 different real answers out of this, right? So we'll get 2 unique real solutions out of this equation just based on using the discriminants, right? All right, awesome. So some things that just kind of push us a little bit further with these. This is just kind of repetitive right here. Find the discriminant of each of the following quadratic equations. Describe the nature of the roots. So whenever you see that terminology, use the nature of the roots. It's getting at, are they real or imaginary? So just kind of like the types of the roots that they are, as well as how many there are. So it's just the same things that we've been seen in the last few examples here. So yeah, you just have to plug in a 0 for y and then, use the b squared minus 4ac to find the discriminant. So this one's kind of special though, because you'll notice that it doesn't have the middle x. So you know that a is 1, but then c is 16. So you have to treat b as being 0 then. So therefore the discriminant is actually going to be 0 squared minus 4 times a times c, which means you get 0 minus 64, which will be negative 64. So that right there would give you the discriminant. Now, if you were to actually describe the nature of the roots, then that means since we got a negative discriminant, then we'd have a negative under the root in the quadratic formula, which means we get imaginary answers. So there's going to be two different ones, right? So the nature of the roots then would be that there are two unique, complex, like zeros or roots or whatever you want to call them, right? That would give us the nature of the roots. And the other example that's right next to that, you'd want to get everything on one side. So let's maybe subtract 6x, and then you get a 0 on that side. So this one's also kind of special because, a is 9 and b is negative 6, but then it doesn't have a c value, so you have to make your c value equal to 0. And then if you do the discriminant is going to be b squared minus 4a and c. So you end up getting 36, and then 4 times 9 times 0 just makes it all 0, so you just minus 0. So you end up getting there 36 would be the discriminant. So now when you got a positive answer, right, that means that you're going to have a positive under the square root, which means it's just real, and you're plus or minusing something. So you'll get two different ones, two different real roots of the expression or zeros of the function, right? So two different real solutions, let's call them. Awesome. Okay, and then here, this just says to find all values of a such that a times x squared plus 3x plus 5 has exactly two distinct real roots. So in order for it to have real zeros or real roots, you want the discriminant to be positive, right? You want that to hold, the discriminant to be positive, which means that you want b squared minus 4ac, just by replacing that delta, to be greater than 0, right? So if we kind of plugged in some of the values that we know, we know your b value is 3. We don't know the a, but we know that c is 5, right? Then we would want this to be true, right? Basically that 9 minus 20 times a would have to be greater than 0, right? And then you can actually solve that to find a. So if you subtracted 9 first of all, then negative 20a would be greater than negative 9. And then if you divide both sides by negative 20, the inequality is going to flip because you're dividing by a negative. Then you're going to get that a is going to be less than 9/20. So it turns out that right there, those are the possible values for a, right? So you could make that number in front of x squared be I don't know, it could be 1/3. 1/3 would be less than 9/20, or it could be negative 504, right? Because that would be less than 9/20. So any number as long as it's less than 9/20, and that would enable it to have two unique real zeros, okay? So if it wanted to be just one real root, that means it would cross the x-axis once. That means that you need the discriminant to actually equal 0. So that means that in order for it to actually equal 0, you would actually need a to equal 9/20 on the dot, right? Just by going through the solving process there. And then finally, if you wanted there to be two distinct complex roots, you would need the discriminant to be negative because you'd want a negative underneath the root. So you would want that to hold, it to be less than 0. So if you went through the solving process of that and flip the symbol, you'd actually get that greater than 9/20 would have to be your value of a. So like 1/2 would be greater, or 1,000,000 would be greater, right? Any of those numbers could be what you make the a value to be in front of the x squared there. Awesome. All right, and then I just want to highlight these graphs here, and then we should be good. So this is asking which quadratic function has a positive discriminant, right? So when you think like positive, like you might think, oh, positive, positive, because those ones are facing up, right? Well, that would have to deal with the a value, right? So when you have y equals ax squared plus bx plus c, then that number right there that I just drew an arrow to would have to be positive for that parabola as well as that parabola, right? But the discriminant, when it's positive, means that the number under this square root, right, is positive, which means that you've got reals that are being plus or minus, so you'd have two unique real answers, right? So when we're looking at the discriminant, you should be looking at the x-intercepts in terms of what we have. So since in this first option here in A, it never touches the x-axis, then we actually know that the discriminant is actually negative. It's less than 0, does not have a positive discriminant. In option B, it touches the x-axis just at 2 only, so 2 is the only real 0 of that function. So that means that the discriminant is actually equal to 0. What you have under the square root in the quadratic formula is actually equal to 0 in that case. It's also the same in option C, because it just hits the x-axis just once, so 0 on the x-axis is the 0 of the function there. But in the last one right here, it's crossing through, it's like -3 as well as 0. And those are the zeros of the function, and they're real. And that is when the discriminant is greater than 0, only when that can happen. So it turns out that this quadratic function is the one that has a positive discriminant.